Structural maintenance tasks are developed as part of the scheduled maintenance process within the MRB. And we understand that there is a structures group within the MRB, and initially, of course, they have a detailed understanding of the installation and the configuration of the structure. What they don't know is how it's going to behave in service. So continually there is feedback from in-service experience together with ongoing testing. And the ongoing testing typically stays ahead of the operation of the aeroplane to determine where the weaknesses will appear. And eventually, after time, we will see fatigue, we will see deterioration, eventually. And of course, the requirement is to stay ahead of this. Mandatory replacement times for structural safe life parts are included in the airworthiness limitation. What do we mean by safe life? Well, a safe life is a calculation that is related to the knowledge that a component will fail ultimately. For example, the landing gear are subject to huge stresses during landing. Each time the airplane lands, you've got huge stress through the landing gear. Eventually, it will fail. In actual fact, the relationship between the typical failure and the safe life is about 500%. For example, we change a landing gear at 12,000 landings, and we know that if we don't change that landing gear and we leave it, it will be typically 60,000 landings, maybe plus or minus 20,000. Means somewhere between 40,000 landings and 80,000 landings, the landing gear will break. But we're changing it at 12,000. So it's way before anything could ever happen. That's what we mean by safe life. And at the end of that 12,000 landings, the landing gear is finished. That's the end of it. So we've got to make sure that it's taken out of service. You can't rework it because that metal has internally been subjected to the stress. There's nothing you can do to make it better. It's not like, for example, we have a flying control actuator, and we use this flying control actuator until eventually it's not doing its job very well. It's getting, for example, it gets hot. Why does it get hot? Because it's got internal fluid leakage. So the fluid is leaking across the inside of the actuator. We take it off, we send it away for overhaul, they take it all apart, they measure the parts and say, oh no, we need that one's worn, so we'll replace it, we put new seals in, we do this, we do that, and we put it back into service. And it's almost, not quite as good as new, but almost as good as new. So it's good to go again. And we will get another several thousand hours out of this actuator, for example. It's not like that with the landing gear or with some of the flap components on some aircraft. Some of the flap components also, when you put the flaps down on the aeroplane, you've got huge air loads and stresses. It's the same story. So when you hear people talking about safe life, what they're talking about is a built-in margin which is significant, typically 5 times related to when it's expected that it would fail. This is what we mean by safe life. Aircraft structure consists of all load-carrying members, including the wings, the fuselage, the empennage, engine mounts, landing gear, flight control, and all related attachments. And if you remember, we said that in terms of understanding the relationship, if the attachment is on the structure, it's considered to belong to the structure. If it's a rotating attachment belonging to the component, it's considered to be part of the component. A structure significant item is any detail, element or assembly which contributes to carrying any of the flight, ground, pressure or control loads, whose failure could affect the structural integrity for the safety of the aircraft. Structure which is judged not to be structurally significant, and of course much structure is not classed as structurally significant. It could be defined externally or internally within the zonal boundaries. So within a zone, for example, we have the stabilizer. And so inside the stabilizer compartment is the outside of the stabilizer. If you think about it, the stabilizer goes all the way through. So we've got an external zone inside an internal zone. It doesn't matter. It's just terminology and understanding the relationship. Additional maintenance tasks may be included to control corrosion to level 1 or better. We keep talking about level 1 corrosion. What do we mean by level 1 corrosion? We actually mean very minor corrosion. And with minor corrosion, we can just clean the surface and re-protect the surface. That's level 1. If, when we look at this corrosion, it's inside the metal, we've got to remove that corrosion. Now, if we're removing it, this is level 2 corrosion, we've got to look at what we're doing, because if we reduce the thickness of the metal, we're reducing the ability of the metal to do what it's supposed to do. Mm-hmm. Eventually, it will finish up so thin that you can poke your finger through it. So, you need to have measurements, and you need to make sure that that level of corrosion, level 2 corrosion, is allowable in that area of the aircraft. If it's non-pressurized area, it makes a different story, of course, to if it's pressurized. If it's pressurized, we've got a difference of 7.5 psi when the aircraft is flying, and again, it could cause a failure. So, level 2 corrosion is quite serious, and it needs to be dealt with in the appropriate way. And I'm not going to say it automatically needs to be reported to the regulator but we need to consider what we're looking at and how serious it is, and then make the right decision. Level 3 corrosion is very serious, and absolutely that will be reported to the regulator as well.